So we'll skip the about me because I already got a nice intro. The one thing that I want to highlight is just this last bullet point, why psychedelics? And there's this great quote from Stan Grof who said, the potential significance of LSD and other psychedelics for psychiatry and psychology and neuroscience, that's my addition, was comparable to the value of the microscope for biology and the telescope for astronomy. And that's the perspective that I'm really coming at this from today. I think psychedelic science is fascinating, for its own sake, but also I think that as a set of tools for understanding the brain as a whole, psychedelics are really one of the most promising tools that we have. So I will briefly talk about, introduce this idea of this critical brain hypothesis, talk about the entropic brain that Robin and others proposed several years ago, and then I'm going to go through two overviews of two projects that I've been working on that sort of demonstrate how this idea of complex systems and network theory can provide insight into how brain dynamics are associated with consciousness. And both of these studies are fairly complex in terms of their mathematics and computational modeling. I'm going to breeze over all of that. There's only two equations in the whole presentation, and they're the same equation. So if you want to go into the really gory details, feel free to ask questions or find me after the fact. But for now, we're keeping things at a very, very high level. And so the two projects are looking at the fractal dimension as a measure of complexity under the influence of LSD and psilocybin. And then I'm going to talk about a different measure of criticality and how that relates to consciousness when comparing two different anesthetics, Propofol and Ketamine. And then I'll talk briefly about why we should care about all of this and what kind of future work we might want to do. So I'm sure most of us are familiar with this idea of the entropic brain hypothesis. Again, it was proposed by Robin and others several years ago. And there's two really sort of key components to it. One is that the vividness of conscious experience is sort of a function of the complexity and the richness of dynamics in the brain. And Chris was just talking a lot about that with the context of the DMT. But one of the other elements is that consciousness emerges when the brain is in this sort of critical zone between two distinct phases. And so I really like this little figure. You've got entropy sort of on the y-axis, and if entropy is too low, you're punitively unconscious. This is sort of similar to states like propofol anesthesia or deep coma. And then if you go too far up, entropy becomes too high, and you are also unconscious. I can't think of an example of what a totally super entropic, highly random unconscious brain would look like, but I suspect it's not fun. And then in the middle, you have sort of this critical zone between the two states, and that normal waking consciousness is sort of in the middle. And then if we take a psychedelic like LSD, you sort of bump up higher entropy, deeper into that critical zone. And the richness of dynamics associated with criticality is reflected in the richness of our phenomenological experience. So when we talk about criticality, we're actually talking about something that's very well defined, coming from statistical mechanics. And so this is a plot that shows a very simple model of a critical phase transition called an Ising model. It's what happens if you heat a ferromagnet. So if the magnet is very cold, all the spins are basically aligned, and this is subcritical. You notice that there's only one scale here, okay? The macro scale dominates. If you zoom in, you don't get any more information. All that you can see is sort of the broad coordination of the elements. And if you go over far end, that's if you're melting your magnet, then there's no macro scale. All you have is the micro scale, and there's no higher order organization. In the middle, at this critical point, you see the emergence of what we call scale-free or fractal patterns. And if you think about those really trippy videos of zooming into the Mandelbrot set, that's really what you're seeing here. If you zoom in and zoom out, the system looks the same. And this emergence of scale-free topology is, considered to be one of the biggest signs of a critical dynamics in your system. Okay? And so if we're interested in quantifying, how critical are these brain dynamics and relating that to consciousness, what we really need is a measure of, how fractal or how scale-free is your system. And this is a good measure because many other measures, for instance, like Lempel-Ziff, it monotonically increases, as your system becomes more random, for instance. But fractal dimension won't do that. It'll be high in the critical state, but low when you're subcritical and have only a macro scale, and also low when you're supercritical and have only a micro scale. So you have this nice U-shaped function that gets at what I think is a more intuitive understanding of complexity. So if we want to relate complexity to consciousness, it's a complicated question. Most of the studies at the micro level, so this would be studies of individual neural networks in dishes or animals, most of that has been done in systems that are probably not conscious. You have a slice of rat cortex in a dish, and you can look for scale-free dynamics in that. Or you have a macaque that has been anesthetized, and you'll still get some signs of criticality. But when you zoom out and look at these sort of human neuroimaging studies, then you do have a really nice relationship looking at things like this 1/f frequency that we think is indicative of scale-free harmonic dynamics. Celine Adesoy and Morten Kringelbach had this really interesting thing looking at connectome harmonics. And then you do have some of these more complex signals like Lempo-Ziff and Higuchi fractal dimension. And so, most of this work has been done on psychedelic human neuroimaging. But if we want to map out sort of the whole space and relate it to these critical dynamics, what you'd really want to see is you'd want to look at a number of different states and see how does fractal character change as consciousness is augmented or consciousness is lost. So part 1, fractal dimension of brain activity under LSD and psilocybin. This is work that was made possible thanks to Robin and Lior, who very generously shared their data with us. Here we use 2 different measures of fractal dimension. One is a temporal measure. So if you look at a time series, you can measure the fractal dimension of that time series using something called the Higuchi fractal dimension. And then if you have a functional connectivity network, which is just a graph representing the statistical dependencies between individual brain regions, you can use a network fractal dimension approach. And both of them use what you might call a modified box counting algorithm. So if you have a shape, a given surface, and you want to find out its fractal dimension, what you'll do is you'll look at a number of different scales. Each scale is represented by LB, that's the length of the size of a box. And then the number of boxes of a given size necessary to tile your shape is just proportional to the size of the box itself raised to some negative exponent. And this negative d is our fractal dimension. And it doesn't have to be an integer, but if you sort of think about what it means for something to be 1 or 2 dimensional, you can see that this is a very simple sort of generalization of that concept. So we used this temporal box counting measure and this spatial box counting measure on functional connectivity networks to see how do these change under the influence of LSD and psilocybin relative to their controls. So really fast, so again, this is data that was provided to us. It was already pre-processed, and so we just did a very simple parcellation. We used the Schaefer 1,000-node parcellation because you need a very large network to do this kind of box counting algorithm on. Find a threshold correlation matrix, which is then isomorphic to a graph, and so we can operate on that graph. So that's sort of how you make functional connectivity networks in 10 seconds or less. And then we used a very strict threshold because we have reason to believe that this fractal character only really emerges when you're looking at the backbone of the network. Results were promising. So compared to the control condition, there was a very significant increase in the network fractal dimension under the influence of LSD. There was a significant increase in the psilocybin condition as well, although if you look at the individual plots, there weren't that many subjects, and there is something kind of odd going down with those last 2. So still trying to figure out exactly what's going on here. The temporal fractal dimension, again, LSD was much more convincing than psilocybin. You get a very significant increase, and the distributions have clearly changed. One thing I want to note about the psilocybin case is that the scans were quite short. They were less than 200 TRs. And so we think that there may just not have been enough information in the time series to capture sort of like a rich fractal dynamic. And to test that, we truncated the LSD condition, which we already know is significantly different when you look at all 700 TRs. And we found that any difference disappeared. So we're tentatively saying that if you had a longer psilocybin bold scan, that perhaps you might see a more robust difference. So our general takeaway is that at least under the influence of LSD, these measures of fractal dimension are indexing a change in consciousness that is related to this fractal scale-free, punitively critical dynamics. And as I mentioned, one of the things, I don't have the data up here, but we also looked at this measure in people who were in persistent coma or had other disorders of consciousness following traumatic brain injury, and we got very similar results sort of in the other direction. So the deeper your coma or the more severe your impairment, the lower the fractal dimension of your bold signals and of your functional connectivity networks. So that's promising as well. We'd like to validate this with richer time series. Bold is very sparse. You're typically getting 1 scan every 2 seconds or so. And so if we had MEG or EEG, that would be something that would be sort of more appropriate for the temporal fractal dimension. It'll be good sort of internal verification of this kind of measure. So then the other project that I'm going to talk about is this signs of criticality in anesthesia, and there is a psychedelic in here. We're not taking a total hard left into a different zone. And actually, really fast, I'm going to stop and show you guys a very quick video. So these are avalanches, okay? And this is not our data, but if you look, you can see that you get these distributions of events. There are a lot of sort of single events that happen, just one-off, but then occasionally you get these very large coordinated bursts of activity that propagate across the whole array. And so these are what we call neuronal avalanches. And a lot of the early work that's been done looking at signs of criticality has been done looking at these kinds of avalanche systems. This is an array that's been put on a slice of rat cortex. So there's probably no consciousness happening here, but there are still critical dynamics. So does everyone sort of grok that? I can play it again if anybody wants. OK. And then F5. Oh, geez. OK, so if your system is critical, these avalanches follow very particular, very stereotyped patterns. And these avalanches can be described by two parameters. One is the avalanche size, which is how many channels or elements participate in the avalanche, a given avalanche. And then you can look at the avalanche duration, which is how long it takes for the entire avalanche to go from start to finish. And if your system is critical, both of these parameters should follow a power law. And so if you sort of think back to the box counting dimension function that I showed you earlier, it's exactly the same thing. You have some function of x, in this case a probability, is proportional to x raised to some negative exponent. And so the fact that you continue to get these sort of power laws, these sort of fractal structures should be indicative of what we might call like a deeper symmetry happening here when talking about these two very different kinds of systems. Okay, and I should say that power laws are not sufficient to sort of demonstrate criticality. There's a lot of other stuff that goes into this kind of analysis and that we are doing on this project, but for now I'm just focusing on this one particular aspect because it's sort of easy to interpret and really does communicate what we're most interested in when looking at these kinds of scale-free dynamics. So to test whether there's a strong relationship between consciousness and signs of criticality, I decided to compare two different anesthetics, and this is trying to sort of control for as many sort of confounding factors as possible. We're comparing Propofol and Ketamine. Propofol is one of the most commonly used true anesthetics. If you ever had surgery, you've probably gotten it. It completely ablates consciousness. There's no dreaming, there's no awareness, you don't have memory of anything. They're just gone. You go down, and immediately you feel like you're waking up with really nothing in between. Ketamine is also an anesthetic. It's also used in surgery, but it allows consciousness to persist in a very interesting way. People are sort of familiar here with this idea of a K-hole, and somebody that's anesthetized with Propofol and somebody that's anesthetized with ketamine, they look pretty much the same from the outside, right? You're just a floppy rag doll that's not responding to anything in your environment. But people under the influence of ketamine are still having very complex dreamlike conscious phenomenological experiences. And so if we wanted to compare, how does consciousness relate to criticality, comparing Propofol to ketamine seemed like an interesting way to go about doing that. And then I should say that Propofol and ketamine, they do have different mechanisms of action. Propofol does many things, but broadly, it increases sensitivity to GABA, the inhibitory neurotransmitter, so it broadly suppresses activity in the cortex, whereas ketamine acts as an antagonist of the NMDA receptor, which then disinhibits other cortical neurons, causing the entire system to just become noisier. All right, so you have two sort of different paths to anesthesia. One is just suppressing brain activity, and one is kind of scrambling it. And you could sort of imagine that this sort of scrambling at very low doses could cause an increase in the entropy or the complexity of brain activity, and that may sort of underlie some of the more psychedelic aspects of sort of mild to moderate ketamine infusion. The data that we used, this is an open source data set from Japan. It's the NeuroTycho data set, and so if any of you are interested in questions of consciousness and want to just play around with some EEG data, this is all free online. You can download it. You don't have to register for anything. You don't have to be associated with any institution. It's really cool. And what they've done is they've taken macaques, they've put in an invasive intracortical array, and you can just record electrophysiological data directly from the monkey's brain as it's anesthetized, as it's awake. They have behavioral data. And this kind of ECOG array is really useful because you don't have all of the sort of problems associated with trying to reconstruct, the source localization that you see like in EEG or MEG, because you don't have a signal that's diffracting through things like bone and other fleshy compartments and all of that. So it's useful if you want sort of very high precision recording. And then, so we had one monkey, his name was Chibi, and he was anesthetized twice with propofol, twice with ketamine, and then recorded during the awake states associated with each of those to let us compare how these patterns of activity look. And the results, also pretty promising. So this, you can sort of think of it as a probability density function. It's not exactly that, but you have sizes on the x-axis, probabilities, modified probabilities on the y-axis. And so if you look at the distribution of avalanche sizes, you can see that ketamine, which is on your left, gray, tracks the awake state much more closely than propofol, which is in gold. And propofol immediately begins to drop down into this more sort of subcritical looking regime. You don't have quite that same nice sort of flat power law fit. And I should say that the awake conditions did pass the maximum likelihood estimation of power law fit. So they're not perfectly straight, but they did pass some basic statistical tests. And one thing that I think is really worth noting is that what you see here on propofol is that what is inhibited are these very large events, that propagate over the entire system. And so if you think about this sort of from a global workspace kind of perspective, you might sort of hypothesize that what propofol is doing is it's inhibiting the ability of events to percolate through the entire system, okay? So it's inhibiting this very broad, activity that recruits multiple regions of the cortex. Everything is just kept sort of small and local. And there's some results from Emery Brown and Laura Lewis, who did some work at MIT, that really suggests that there is something to this, that when you're anesthetized with something like propofol, locally circuits are behaving the way they always have. It's this sort of large-scale coordination that becomes inhibited. And you don't see that with ketamine. And so, again, in a global workspace context, you might believe that as consciousness is perhaps related to the ability of information to percolate through the entire system. Here we have avalanche durations. These are never look as good as the avalanche sizes, but again, you see that ketamine tracks the conscious state much better than propofol does, which again immediately begins to diverge from the distribution of avalanche durations. So interpretation of this, you could think that the avalanche dynamics under the influence of ketamine look more like the avalanche dynamics you see in the awake state when compared to propofol. And one thing that I think would be really interesting to do would do this same analysis on human neuroimaging data of LSD, psilocybin, DMT. You need fairly long scans for this, and so a stationary signal like LSD or psilocybin might be better than something like DMT, which is a very non-stationary process. But I suspect that coming back to this, you might get something sort of like that looks like almost the opposite of ketamine. You might get a pile up of very large events down here as the entire brain is recruited to events, recruited by events that sort of ordinarily would not percolate through the whole system. So stay tuned for that, hopefully. And then, like I said, all these, the question of like how do you define a power law, what makes a system critical is sort of non-trivial. And there is a lot of stuff sort of on the back end of this that I'm not talking to. But if you are a statistical physicist or a power law expert and want to berate me, you are welcome to do that after the fact. But we are doing more. We're looking for things like exponent relations and shape collapse of the avalanche profiles and all that kind of stuff. So, and then finally, this is just like a little bit of a pitch for complex system science. Hopefully, I'm trying to recruit some more people to look at the brain using this paradigm. The brain really is like a paradigmatic complex system, right? It is a scale-free, basically object where at any scale, the dynamics that you see are an emergent property of the scale immediately below it, okay? And the thing that I think makes psychedelics so fascinating as a neuroscientist is that they're really one of the only ways that you can look at the whole system through all the hierarchies. You flood the brain with something like LSD, and what the LSD is doing is working on that very micro scale. You have little bundles of carbon that are interacting with other little bundles of carbon, and that's it. But somehow, the signals that are caused by these little bundles of carbon interacting with each other, they propagate up through the system. And if you look up at the Meso scale, this is Giovanni Petri's famous plot, you have something happening that's changing the mesoscale dynamics that you couldn't necessarily predict, just looking at one bundle of carbon and another bundle of carbon coming together. And then somehow this mesoscale dynamics give rise to our complex phenomenology. And it's my favorite little Alex Gray painting down there, Wonder. And other methods of approaching the brain, top-down task-based paradigms or sort of, very low-level biochemical paradigms, they miss that there's this like thread, that runs through all of the scales. And so complex systems, which is, a science designed to look at multiple scales, really provides, in my opinion, sort of the best way for neuroscience as a field to move forward. And I think that psychedelics, if we sort of play our cards right, could be, a key facet of this ongoing research program. So thanks to the teams that are working with at Cambridge, the Cognition Consciousness Imaging Group, particularly my mentor, Emmanuel Stamatakis, Darwin College, then the Imperial Psychedelic Research Group, particularly Robin and Lior, who provided some of the data. And then also the team that I'm working at Indiana University, one of my mentors, Dr. Olaf Sporns over there. He's in psychology, and then Dr. John Beggs and YYN, who are in physics and complex systems. And of course the NSF and the Wellcome Trust, who have given us money to do all of this kinds of research. And so the last thing I'll do is, this is a totally shameless plug. If you feel like supporting an early career scientist, we can't really collect this data over in Indiana. They're not big on that over there. So if you have psychedelic neuroimaging data, or you're interested in complex systems approaches to neuroscience, please email me. I am always interested in collaborating and talking and trying to bring complex systems neuroscience to the world. So thank you.